Hey everyone, and welcome. Today, we're going to talk about something called strain. Now, it might sound a little technical, but it's really just the hidden language materials use to tell us if they're about to bend or if they're about to break. So let's dive right in. So, have you ever really stopped to think about this? When you bend a paperclip or stretch a rubber band, what is actually going on deep down inside at the particle level? It's a pretty fascinating question, right? And that's exactly the mystery we're going to start unraveling today. Okay, here's our game plan. We're going to start super simple with just basic movement. Then we'll figure out how to measure it, and from there, we'll build up to this really powerful tool called a tensor. By the end, you'll see how it all boils down to just two fundamental ways any object can truly change its shape. All right, first things first. We have to start at the absolute beginning. Before we can even talk about a whole bridge deforming, we've got to understand what happens to just one tiny single point. So take a look here. You see that point A? When we apply some force, it just moves, right? Over to this new spot, A prime. That little arrow connecting them, that's what we call displacement. Now here's the key. If every single point in an object moves the exact same way, the whole thing just slides over. No big deal. But the second one point moves differently than the point right next to it, that's when we get deformation. And that, my friends, is where all the interesting stuff happens. And this is a really big idea. It turns out that any kind of movement, no matter how wild and complicated it looks, can always be broken down into just three simple parts. You've got a slide, which we call translation. You've got a turn, which is just rotation. And then you have the part we really care about, the true change in shape, the distortion. So why is this so important? Well, think about it. If you just slide a book across a table or spin it in the air, you're not breaking it, right? Those motions don't cause stress. It's only that third piece, the actual distortion, that can cause something to fail. So the whole game, the entire purpose of studying strain, is to find a way to mathematically ignore the boring slide and turn and just zoom in on that shape change. Okay, great. So we know we need to focus on just the distortion, but how do we actually measure it? How do we put a number on it so we can do some math? Well, that's exactly what we're going to cover next. There are basically two fundamental ways to do it. So the first one is called normal strain, and honestly, this is the one you already get intuitively. It's just stretch or squish. You take how much the length changes and you divide it by the original length. It's that simple. You pull on a rubber band? Yep, that's normal strain in action. The other type is a little different. It's called shear strain, and this one isn't about length, it's all about angles. The best way to picture this is with a deck of cards. You know, if you put it on a table and just push the top card sideways, the whole deck leans over. See how those perfect right angles at the corners get all skewed? They're not 90 degrees anymore. That change in the angle, that's shear strain. All right, so now we have our two main building blocks, right? We've got normal strain for all the stretching and shear strain for all the angling. So what's next? Well, now it's time to combine them, to put them all together into one powerful tool that can describe everything that's happening at any point inside a 3D object. And here it is, the strain tensor. Now I know that word tensor can sound a little scary, but for today, just think of it as a super organized box, a container. Instead of just pointing in one direction like a simple arrow, this box holds all the information about every stretch and every shear in every direction all at once. Yeah, it might look like a grid of numbers, but it's really the complete story of deformation happening at one single point. And the way you read it is actually way easier than it looks. There's a simple rule. For any of these little e's, the first letter tells you which face of a tiny cube you're looking at, and the second letter tells you the direction of the strain. So E sec x, that's on the x face in the x direction. See? It's a stretch. How about EXY? That's on the x face, but in the y direction. That's a shear. Once you get that little face direction rule down, you can decode this whole thing. Okay, we are getting so close. We have this amazing tool, the tensor, that measures everything. But wait, remember what we said at the very beginning? Our most important rule? We have to throw out any part of the movement that isn't real deformation. Just think about a spinning wheel on a car. Every single point on that wheel is moving like crazy, right? It has a huge displacement. But is the wheel itself actually stretching or breaking? No, it's just rotating. And for an engineer, that's a world of difference. You absolutely have to be able to separate a harmless spin from a dangerous strain that could cause a clack. And this is where the math gets really, really clever.
It turns out you can take that full tensor of movement and split it perfectly into two pieces. One part, called the symmetric part, contains all the good stuff, the true strain, all the stretching and shearing. The other part, the anti-symmetric one, contains only the rotation. So what do engineers do? They just throw the rotation part away and focus on the part that actually matters. It's so elegant.
Okay, so we've done it. We've isolated the true strain. We've gotten rid of all the noise, and now we are ready for what is, I think, one of the most beautiful and powerful ideas in this whole field. Seriously, this is the big aha moment. And here it is. Get this. No matter how you twist, bend, stretch, or crush an object, no matter how complicated it seems, the deformation can always be broken down into just two simple things: a change in its volume and a change in its shape. That's it. That's the whole story. The total strain is just the sum of the volume change and the shape change. Incredible, right?
So let's break that down. First up, volumetric strain. The best way to think about this is to imagine a little foam stress ball. If you could squeeze it perfectly evenly from every single direction, what happens? It gets smaller, but it's still a perfect ball. Its shape hasn't changed. That is volumetric strain. It's nothing but a change in size.
And you know what's cool? Calculating it is surprisingly easy. You just go back to our strain tensor, grab those three normal strains, the stretch along the x, the y, and the z axes, and you just add them up. That's it. That one number tells you the entire change in volume for that point.
Okay, so what about the other piece? That's called deviatoric strain, and it's basically just everything else. If you take your total strain and you mathematically subtract out that simple volume change we just found, whatever is left over, that's the pure, unadulterated shape change, the distortion. This is the part that twists and warps things, and a lot of the time, this is the component that tells you when something is about to fail.
Whew, okay, we have covered a lot of ground, haven't we? We went from a single little point moving in space all the way to this complete picture of deformation. So let's wrap it all up and recap the three biggest ideas, what I'm calling the three pillars of strain. Okay, pillar number one. The most important thing is to separate the real shape-changing strain from the boring stuff like just sliding or spinning. Pillar two, we built the perfect tool for the job, the strain tensor, which is our one-stop shop for describing every possible stretch and shear. And pillar number three, the big one. Any deformation, no matter what, is just a simple mix of volume change and shape change. That's the core of it all. So this leaves us with one last massive question. We now have this perfect language to describe exactly how something deforms. But how do we connect that to the forces that are causing it? How do we use all this to predict the exact moment something is going to snap? Well, that is the bridge to our next topic, and that's a story for another explainer.